Okay, so I think we went through some of the stuff last time very quickly, and do you guys want to start all the way from beginning, or we should start from where we left off last time? Up to you guys. Anyone has any thoughts?
Oh, okay. So why don't you recap what we've done so far, just briefly, and then continue on with.
Okay, that's a good idea. All right, so let me recap. Basically, what we did was, okay, let's just loading the data. And what is the data itself? It's the Portuguese English translation data set from the TED Talks. And what does the data look like? We got 50,000 training examples, 1,100 validation example, and 2,000 test examples. And this is how you load up the data. And we were just taking a look at it. And let me just shift enter it through myself as well. And for those of you who are new to Colab, if you don't link to your own like Google Drive, you almost always have to install the package. Just so you know, because every time you install it, it's not installed locally. So.
Sorry, could I just ask, the notebook you're running there, is that just your own copy of the Transformer notebook?
Yes.
All right.
The notebook.
So that's why it's got the different. That's why it's got the different titles, just because it's your saved version of it.
Yeah, exactly. So you should always save a copy of your own, and regardless, you almost have to, because you can't save it somewhere else. You have to save it in your Google Drive.
Okay.
For whatever you want to save, you know, even if it's just comment, adding a comment, you want to save it somewhere. Yeah.
Oh, cheers.
Yeah. And here's a glimpse of what the data looks like. Again, this is Portuguese, this is English, and we talked about it, right? This gets inputted into the encoder, and this gets inputted into the decoder. The sentence that you want to translate into gets input into the decoder. The sentence that you want to translate from gets inputted into the encoder. Okay. And this basically just helps you to tokenize. Then you can encode that as well. And just some quick encoding, adding the start token and end token to the input and targets. Filtering out for the sake of the example, the notebook filters out the examples with a length of over 40 tokens. So they're basically building a function for that, and prepare your data sets, training data sets, validation data sets. And each of your
Wenchang?
Yep.
Okay, you know, we're doing this like a big map filter job. Do you know at a, you know, if at a high level what exactly that achieves?
Map filter job.
A map filter. So if you just look at the bottommost cell on the screen you're sharing at the moment, there's this big map filter piece of work. Do you know what that's doing?
I believe this is filter this, right? So we want to filter out dropping the examples with a length of over 40 tokens. So if X is smaller and equal to 40, we keep that. So we filter that out. and that's that padded batch, and you just batch it. I guess that's what it is, and with the batch size. Is that clear?
Yeah, yes, it is. Thank you.
Okay, great. And as you can see, it got to 39 instead of 40. So I guess there probably isn't a sentence that's exactly 40. So it dropped to like 39, and then it's padded. So that's that. Yeah. And okay. We went through positional encoding, basically how we can build a function for that. And this is just that part, get angles, and then we feed that into a larger function. And for the even number, we use sine. For the odd number, we use cosine, and then you numpy.sine, and you feed that function into this, and into that, and eventually you will be able to encode your positions. So we went through that, so I'm going to go through this relatively quick. And we also went through this masking. Again, masking just helps you to ensure that the model does not treat padding as input. The mask indicates where pad value 0 is present. It outputs a 1 in those locations and a 0 otherwise. And if you look at that example quickly, 7.6 gets padded to be, gets masked to be 0, 0.0 gets masked to be 1.1, and you want to shape it in the structure that your transformer architecture can use it, and it's 4-dimension. So you add 2 extra dimensions for that, and this is the new axis, right? You're adding extra dimensions to add the padding.
So one more question for you, Wencheng. You know, there's this image that you have above. So this one, why is it helpful? What is it supposed to tell us? Because it's not. I don't see what's the point of this.
It's just literally mapping the numbers with colors. Anyone else wants to chip in?
It's the same as the one that's in the illustrated transformer page. Effectively, yeah, like so each row with that is like a timestamp that you join with the actual embedding for the word. So it puts the timestamp onto the embedding to show what position it is on the input data.
Mm-hmm. Yeah. So
I was wondering, like when you combine this sort of timestamp vector with the embedding vector, you would think it would like sort of modify the embedding vector and sort of change it. I wondered why they just didn't sort of like have a field in the embedding vector to have a number which would say its position in the input string.
Yeah, that's a good point. I still haven't completely grasped the idea of that positional encoding. But I think what you said, Steve, is a really good way to put it. Is that it puts a timestamp onto the embedding. In other words, it encodes the position within the sentence of that word. And I think so. If we think of it as a black box that just does that, as Steve said, puts a timestamp on each word. A timestamp in a sense of being an order within the sentence. So, you know, the first word in the sentence, the third word in the sentence, the 17th word in the sentence, so on. I think it's best if we think of it that way. before we try to understand the guts of it. And I think that it's a good way to think about it as a timestamp.
Yeah, you can see from
sorry.
this,
So
you can see from
what?
this picture as well that it sort of it varies very slightly from one step to the next, and so it's easy for it to work out sort of the relationship between each time period.
Stephen, could you give an example? So, because I still don't understand what it's showing. So,
Sorry, Wen-Chen, could you go up just slightly more, slightly above it? It shows the different. It shows how the embedding vectors combine. Yeah, there. Yeah, so here you can see like the three embeddings, the x1, x2, x3, those are the actual embeddings for each word that's coming into the encoder. And then to combine it with the positional encodings, which are from the picture below. So you can see the first word, it gets combined with 0011, which is a unique timestamp for period 1. Then the next one, it's slightly different. So like that's a unique timestamp for the second period, and similarly for every timestamp. And like the neural network, it learns effectively what the timestamp relates to, and then it can understand the position of the various words that are coming in. Because like obviously if you're like in an LSTM, you put one word in at a time, and so it knows the position of the words in the sentence just from the order they come. But because of the fact that all the words are coming in at once, it needs to put these timestamps on so as it knows what the position of each word is.
Yeah, I think the last thing Steve said is very important, John. In attention, you lose any concept of sequence. So you have to reintroduce the concept of a sequence. And this helps to do it by stamping the positional sequence on top of just the natural embeddings that you get. It reintroduces the sequence concept.
Sean,
Yeah, but I'm thinking of what Steve said first, which is why don't you just add another field that just says, word number 1, a few more bits to the encoding, and then you could encode the position in a few bits, whether it's number 1 or number 40 or number 20 or number 25. In this way, this is what I don't understand about positional encoding, is that when you combine that positional encoding vector with the word vector, with the encoding vector for the word, now you're mapping that word to a different position in the space of words. And so, in other words, in the vector space of word embeddings, you're distorting that vector and pushing it somewhere else in that space of word embeddings. So I don't understand how that works, unless there's a unique way. Maybe there's a unique way to. Well, maybe this is how it works, because each one of those positional encoding vectors is unique. You can easily decode by subtracting it from the word once you figure out what position it's in. But in some way, you have to map the word. You have to work with the embedding space, original embedding space of the words, because otherwise, how would you get meaning out of the words if you constantly distort them and push them into a different area of the vector space? I don't know if that was clear or not, but that's what I wonder about.
So I think one of this person, I don't remember where I got this blog from, but this person actually mentioned it, and he said he wasn't able to find any theoretical reason for the summation instead of concatenation. And since summation contracts to concatenation, saves the model's parameters, it's reasonable to reform the initial question to does adding the imposition embedding to words have any disadvantages? I would say not necessarily. So I guess empirically they found out it's not necessarily a disadvantage. And since the embeddings in the transformer are trained from scratch, the parameters are probably set in a way that the semantics of a word does not get stored in the first few dimensions to avoid interfering with the positional encoding. With the same reason, I think the final transformer can separate the semantics of the words from their positional information. Moreover, there's no reason to consider the ability is an advantage, maybe the summation provides a good source of feature for the model to learn from. So that's what this person's explanation. Now, I think back to John's question, John, I think you were trying, I think you have a little confusion over like what this graph, what the heck is graph. It's just color coding literally the values of your arrays, and between 1 and -1, and this is the, I believe, this is the sign, the outputs from the sine function. And this is the outputs of the cosine function, and the length is 512, right? 512, and that's your D model, the dimension of the model, and this is each word. So each word has 512 numbers, right? And you literally encode that, and also each word itself throughout the sequence would have different numbers as well. So that's that.
Okay, I need to think about this a little bit more, but thank you. Thanks, everyone, for your.
Okay, so masking, we talked about that already. And the create look ahead mask, and this is just to make sure your model does not look at the information that it shouldn't look at, and it's used to mask the future tokens in the sequence. And if you look at this, so it gradually, basically takes out one, basically 4 1s, 3 1s here, 2 1s, 1 1s, and so it means that to predict the third word, only the first and second word will be used. So basically, it sort of demasks at each row. Similarly, to predict the fourth word, only the first, second, and third word will be used, and so on. And that's what the language model is. So, okay. Scaled up product attention. I guess we should probably spend a little more time on this in terms of the code. And let me just run through. I didn't shift enter through this, so let me run through this. Okay. So scaled up product attention, it's basically this, right? This formula, mathematical formula. And again, if you reference J. Lammers, it's this, right? And if you reference the paper, it's right here, scaled up product attention. So the way how this is coded is you specify the QKV as parameters, and you have the mask right here. And note that the mask is multiplied with -1 E9 close to -infinity. This is done because the mask is summed with scaled matrix multiplication of Q and K and is applied immediately before a softmax. The goal is to zero out these cells, and large negative inputs to softmax are near 0 in the outputs. And the Q and K have a mean of 0 and variance of 1. Their matrix multiplication will have a mean of 0 and variance of dk. Hence, square root of dk is used for scaling and not any other number, because the matrix multiplication of Q and K should have a mean of 0 and variance of 1. You get a gentler softmax. Okay, so now it explains why you actually need to scale with dk, dimension of k vector. It's because when you do matrix multiplication, you have a variance of dk, then you scale down back to 1. Okay. Okay. And K and V must have matching dimension. Sequence length K equals to sequence length V. The mask has different shapes depending on its type, padding, or look ahead, but it must be broadcastable for addition. Okay, that's, and QKV all should have matching leading dimensions. So query shape Q should be sequence length Q, depth, key shape, sequence length K, depth, and depth is D models divided by number of heads, right? So 512 divided by 8, that's 64. We use batch size of 64 as well, so don't confuse this 64 and the batch size. It can be confusing. And same thing, sequence length V, depth V. Okay, so matrix multiplication, you want to just matmul Q and K, which is this step, right? Q and K. And you scale matrix, you reshape that to get, sorry, you get your dimension of K. That's how you get that. And you scale that, then you get your scaled attention logits. And that will be this step, right? This denominator divided by the root square of dimension K. And that's this step. If the mask is not none, so if we passing a mask, we mask that, okay? Then you mask the scaled attention logits, and it's right here, right? So when you, after you scale, you mask it before you softmax it. Okay, then you softmax it. Okay, attention weights now equal to tf.nn.softmax. Scaled attention logits, you pass into that, axis equals to -1. You basically you softmax along the axis of this. That's the -1.
I've got a question. So you know, when we started off, we said Q, K, and V all have dimension of 64. So what do we mean by a sequence length of Q, K, and V?
Sequence length, remember we have sequence length, I believe this sequence length is if I remember correctly, this should be well, is that this let me think about it. Sequence length 64. It should be the, correct me if I'm wrong, but it should be the column numbers of Q, K, and V.
Is the number of words right?
Number of words. Yeah, it should be number of words. But
I think it's 512 in this model.
It is the number of words in the sequence. The sequence is what you chop the the entire corpus into, and then you create batches from it. So it's the number of words in the sequence.
So then they're the same, right? For Q, K, and V. Why would you have different? That's just confusing that you'd have different variables. Am I oversimplifying it?
They're the same, but they mean different things. They have Q, K, and V have the same length, but they mean different things.
No, so I mean, no, what I meant is about the, so if you're saying the sequence length is just the number of words, why would you have different variables for each of them when it's just the number of words?
No, the variable isn't the number of words. It's the key. It's query, key, and value. They mean different things.
Yeah, I know Q, K, and V are different things. I'm just referring to the sequence length Q, K, and V. If you're saying those are the number of words, why would you use a different variable for all of them if it's actually the same number?
So in the encoder decoder attention, you might have different sequence length, right? When you're attending from the decoder to the encoder. So in that case, you would have different sequence length. So I think they may be reusing the same function for both types of attention. So that's why they have kept it as a separate thing. Maybe. In that case, it's really useful, right? To have general QKV.
Can you say that again, please? I didn't understand why those things would
Okay,
change.
I'm just giving an example of when sequence length would not be the same. I don't
Sure.
know if it's relevant to this. So yeah, in self-attention, you are see all. I mean, all Q, K, and V are projections of the same input embedding, right? You are just attending to the same sentence.
Yep.
Whereas in encoder decoder attention, the attention is from the decoder to the output from encoder. It is not self-attention anymore. So in that case, the query comes from the input to the decoder, whereas key and value are projections of the output from the encoder. So in that case, the sequence length would be different.
Yeah,
Like
if you see, he uses exactly to your point, Gautam, the sequence length of K is made equal to V, but the sequence length Q is left separate for exactly the reason.
Key and value would always be have the same sequence length, but query could be different when it's not self-attention.
Yeah, I in the decoder, yeah, I would agree. And I mean, it's also good coding like habit to name it differently, regardless. And it's just clear to do that. Okay. So back to this, and hopefully this sequence length will become clearer when we get to the later parts of the code. I know it could be a little confusing right here, but hopefully will become clearer. Okay, so then basically in the end, you matrix multiply attention weights from this one with the V, and this goes back to this step, right? So after you're doing the softmax operation, then you matrix multiply with V, then you get your Z. And note that this in the transformer has already been split. We're just doing this, right? So in this case, the QKV has already been split. So that means the column numbers is already 64 instead of 512. It's just, it's not showing here because we're only doing the calculation here. We're just taking whatever it is and do the calculation. And you split in the multi-head attention. But after you splitting, then you feed it into the scale dot product attention. Okay. This is just testing with some numbers, with some temporary numbers, with examples. Okay, so multi-head attention. we're initializing, we're inheriting from the tf.characters.layers.layer, and we're setting the number of heads equals to 8, dimension of model equals to 512, as we said. And you know, you want to make sure 512 can be divided by your number of heads. If you know, you can't choose 10 heads with 512, right? Because that's not dividable. And so that asserts, make sure you don't do that. Okay, so 512 divided by 8 equals 64. And that's equivalent to dimension of dk and dv. Again, as I said, the columns of your k and the columns of your v would have to be split. And that's your depth. Okay, so and we want to create the dense layer, and this is the embedding to be trained, right? This is the weights. And when we look back to that, this is the self.wq, self.wk, self.wv here. And the way how you do that is just, you know, use tf.characters.layers.dense, and then you can train. And this is dimension, right? D model. Okay, self.dense, and then there's another dense, self.dense right here. And I think it's passing at the end. Yes, it's passing at the end. Okay, so split heads, and this is what we have been discussing, like how does it actually get split? And in the end, it's just a dot reshape, right? So you're not actually like separating them, you're just reshaping them by splitting this 512 into 8 by 64, and 8 number of heads and 64 as your depth. So you have 64 as your batch size, and you leave the final dimension to be calculated by TensorFlow itself. And you want to have 8 number of heads, and you have your depth at 64. That's just calculated by 512 divided by 8. And so you have a 4-dimension instead of a 3-dimension array now, or tensor. And tf.transpose, then you just transpose that to make it, you know, 0 to 1, 3. So you want to have 0, keeping the batch size here, but you wanted this to be the 0, 1, 2. You wanted this to be here. You want this to be here, and keeping self.depth at here. Okay. Define a call function so that this can be called and do the calculation actually, because this is just defining a function to split the heads, and you call them under this function. And batch size, tf.shape.q. So basically, whatever you're passing, right? QKV, they should all have a batch size of in this case 64, and you just query that. Now, then you pass in your input to that WQ, which you define here, right? So again, I think we mentioned it a little bit. This X, this part of X is actually the Q here. And this part of the X is the K here. So it's not named in a way that it's very intuitive, but it can be confusing. And this V is the input for the V. Okay, so then you times that weight embedding, right? Then you get your actual QKV vectors, and this is what you get, right? So I think, yeah, the naming of the variables is a little confusing here. Okay, then you split your heads. So what do we have here? We have literally 64, right? 64 and sequence length. I think we dropped the sequence length to be like 40 or 40 or less. So we have like 40 or 39, I believe. Then your D model is 512, right? So this is the tensor shape. Then you basically split that into 64 and 8. Okay, 40 here, 512 and 64 and 8. Okay, and remember we did the transpose. So number of heads becomes the second position, and self.depth keeps it, keeping your self.depth at last, keeping your batch size at first, and you let TensorFlow to calculate this, and then this -1 is actually the sequence length Q, and your sequence length K, and your sequence length V. Okay, so this, I guess, back to your question, John. This dimension is actually just calculated by TensorFlow, and it's not something that you set in this case, because it's -1. The -1 is here, so it's reasonable to separate them out. Okay, and then you call this previous function, right? You call this scale dot product, right? After you doing the split, after you did the split, you call this function scale dot product attention. In the graph, so when we calculate that, you do the split. So you basically split this, okay? Then you call this function to do the calculation. So these are already splitted. Okay, so and yes, you call that, then you get your scaled attention, your attention weights, you transpose that again and to reshape that, and then you reshape them back, meaning concatenating all the heads together. Okay, so now you're doing this step, right? Concatenating them together. So you're back to 3 dimensions. You're back to 3 dimensions instead of 4 dimensions, right? So after concatenating, you have your batch size 64, sequence length Q, D model 512. And we'll have to see what the value is for the sequence length Q here. Okay, so then you finally pass in another self.dense. You have another dense layer, and this is the WO, right? This is the self.dense. So eventually, after you concatenated that, you have another linear layer. Then you pass in this X, which is self.dense. Sorry, WO, which is self.dense, and you get your final output. Okay. And this is just, I was just doing some reshaping, trying to find out what the -1 does. And I guess we can go through it a little bit here. I was just testing t, if t equals to like 2 by 3, right? And if you do that by 2 and you don't know what your dimension is, it would just get you 2 by 3. And if you want to do like -1, 2, and it would just set this as 2 and it will calculate this as 3, right? Because it's, you have 6 numbers and 6 divided by 2, that's 3. And in this case, if you want to set this, the first dimension is 6, and it will automatically calculate the second dimension for you, which is 1, right? So that's that. That's what the -1 does. It just, you let TensorFlow to calculate the dimension, because that dimension is almost fixed if you set one dimension or set enough dimensions and leaving the last dimension to be calculated. Okay, so again, this is just testing some with some randomly generated numbers to see how the shapes get transformed. Okay, so now we're getting to the position-wise feed-forward network. So remember, we have self-attention, which we just went through, and layer normalization, and we have a position-wise feed-forward neural network. So that's the step that we're looking at right now. And in a paper, we're looking at right here, position-wise feed-forward network. That's what we're implementing right now. Again, it's one linear matrix multiplication plus bias, then you pass into a ReLU activation function, then you have another layer, right? And so the way how it's implemented is exactly that. You pass into a dense layer, which would allow you to do x times w1 plus b1, and that's what it is for the dense layer. And you just set activation as ReLU, okay? And sorry, that's what max 0 does. And you pass into another dense layer, right? Another dense layer will allow you to do W2 plus B2. And that's what this is. Okay, so you literally just have your sequential 2 layers with the activation in between. And that's what it is. Okay, okay. So now we're gonna we have the sublayers, right? These are feed-forward multi-head attention. These are sublayers. Okay, we have the sublayers. Now we gotta code the entire encoder and code the entire decoder with the each sublayer incorporated. So okay. So each encoder layer, again, consists of 2 sublayers, right? Multi-head attention with padding mask and a position-wise feed-forward networks. We went through these 2 previously. And each of these sublayers has a residual connection around it, followed by a layer normalization. Residual connection helps in avoiding the vanishing gradient problem in deep networks. The output of each sublayer is layer normalized, right? So that kind of refers back to the paper right here. So each output of each sublayer is layer normalized right here. And the normalization is done on the D model axis, the last axis. There are n encoder layers in the transformer, and in this case, n is equal to 6, right? Decoder is also equal to 6. Okay, so let's go through this. We got an encoder layer as a class. Okay, we inherit again from tf.characters.layers.layer. Okay, so then we super that or initialize that. We initialize this, right? So that we can inherit from that class. And look at this. We're calling the multi-head attention class. We're initializing the multi-head attention class we built above, right? This one. We just built that. We're calling this class. And we're initializing with D model and number of heads, right? So, and instantiating that class to pass into a encoder layers instance method, self.mha, with D model equals to 512 and number of heads 8. And we are also calling the position-wise feed-forward neural network, D model and DFF. I don't know what this DFF is. It's 2048. 2048. I don't know why it's set as 2048. Let's see what this is. 2048. Okay. Does anyone know what this DFF is? Perhaps.
I think that's the number of nodes in the hidden layer of that feed forward, right?
Yeah.
So from 512, it goes to 2048 and then back to 512, I think.
Got it. So it's probably the hidden layer, hidden units, you're saying. That's what it is.
Yep.
Number of hidden units. Okay. I wonder why they chose 2048. Okay, well, okay, that's thank you, Gotham. So self.layer norm. So we define 2-layer norm, and we call the tf.characters.layers.layer normalization. And I think there's an epsilon as a parameter you can pass in, and we define 2 of them because we need 2 of them, and then we have 2 dropouts. Okay, again, we're inheriting the dropout and layer normalization from this class, which we initialized here. And we're passing the rate that we want to drop out, and it's usually 0.1. That's the standard dropout rate, right? Pretty straightforward stuff. And we want to define a call function under that class. Attention output equals to self.mha, right? So we're passing that, we're instantiated that, then we're passing in xxx mask. So
hey, Wenchang, sorry, just a quick question. You know, you said it's really standard that you do a dropout of 0.1, and that was really standard. Where else have you seen that? Because I've always seen it as half in CNNs.
Yeah, that's right. CNN like models, I normally just see like dropout as 0.1, and when I was doing fast AI, it's usually dropout equals to 0.1.
Okay, great. Okay,
Yeah,
thank you.
so the answer is I've seen that from fast AI. Yes. Okay, and notice it seems like the inputs are all the same for QKV, right? Which is, yeah, so it's all the same. So let me just go back to that graph. This is all the same, actually. This is different, obviously. This is initialized differently. And so your QKV get calculated different because of that. But this is actually the same. Because you see this, XXX. And again, the reason why I said this was poorly named, because he literally just or someone literally just passing XXX as VKQ's input, right? So this is X, this is X, and this is X. And only when you after you do the matrix multiplication, then you get your QKV. So I think this was poorly named. No, my runtime literally just is up. Okay. Let me. And okay, then you have your dropouts, attention outputs. You pass into the dropouts with this layer. Training equals to training, so you pass in the I don't know what this training is, but
because you wouldn't have dropout in test. I mean, when you're predicting, right?
Yeah.
You would have dropout only when you're training.
Ah, okay.
Yeah.
Makes sense. So if it's not training, if you're just like doing testing, then of course you don't need dropouts. Yeah. Makes sense. Outputs 1 equals to self.layer norm. And again, this is what we were talking about. This is exactly this, right? Layer norm X plus your outputs, right? Attention outputs. So you get output 1, and you pass that into the feed-forward neural network right here. Let's just go back to. So after you do the layer normalization, you pass into the feed-forward neural network, right? Which is what we did here. Then you drop out again, right? And then you layer normalize again. So there's another layer. There's a 2-layer normalization, right? Remember we have self.layer norm 1, self.layer norm 2. So we have the second layer norm, and you have the FFN output. You pass in this FFN output into this. Okay, and then you have your output 1 here. Then you self.layer norm 2 of that. Then you get your output 2. Then you eventually return your output 2. That's your encoder layer. Decoder layer. Okay, well, I think we're good on time. Okay. Each decoder layer consists of sublayers, 3 sublayers, right? Masked multi-head attention. Multi-head attention with padding mask. V and K receive the encoder output as inputs. Q receives the outputs from the masked multi-head attention sublayer. So Q comes from this, okay? K and V comes from the encoder, which is above. Then you have position-wise feed-forward network. Again, let me just do this. Right, so decoder only takes in encoders K and V, right? K and V. And it gets passed into only the encoder-decoder attention, which is the second sublayer here. So only the second sublayer encoder-decoder attention takes in the V and K from the encoder. And the Q comes from the previous output. Comes from this, right? The Q of this comes from this. And you have a position feed-forward neural network, and the rest of it is just layer normalization, right? Add and normalize. So you have an add and layer normalization. Okay, is that clear?
Hey, sorry, I do have a question. So the decoder on the right? We said that right at the bottom, those inputs are
English sentences
Right.
from decoder.
How come? So the inputs are English sentences.
Sorry, what was the question?
Yeah. So how come we're not seeing that in our call to the functions?
We'll see that, but remember at the beginning, we literally have, this is the Portuguese sentence, this is the English sentence. And it's all in a tuple. This is a tuple and this is the Portuguese sentence, this is the English sentence. So this gets feed into this and this gets feed into this. But if you're only doing GPT, right, which is decoders only, then you're only having English sentence and you're just predicting the next word. Is that clear?
Yeah, I think I'll just wait for us when I can see that bit. So okay, perhaps my question's a little premature. Thanks.
Yeah, that question, it will come later on when we actually do it. You know, probably, yeah, it'll come probably a little later. You're right.
No, it was just a bit odd that you're talking about the inputs of the decoder and you're not and they were just not referencing the second part of the tuple. So
Got it. Okay. Okay. Yeah, we'll probably see that in the code. Okay. And again, we're passing in the tf.characters.layers.layer, and we initialize that this class, and now we have two multi-head attention. Okay, so I think we were talking about, is this really multi-head attention? Yes. So this is a multi-head attention, and this actually, I believe this is also self-attention. So I think Gotham, I believe this is also self-attention. It's just, it's taking the outputs different. It's taking the inputs from a different
Not that
place.
one. I was talking about the one above that. So there is an encoder decoder attention above that, right?
Yeah, but this is this. This is self.image1 and self.image2.
Yeah.
So you
So
would, yeah,
go on.
yeah. You will see here. This is the this is still calling the self.image2, MHA2.
Yeah, but it's not self attention because you are getting the key and value from the encoder
Okay.
output.
Okay, so yes, in that way, technically, yes, it's not like attending to itself. You're right, but it's calling the multi-head attention class.
Yep, we are reusing the same functions.
Yeah,
yep.
It's structured in the same way. Okay, so and you can see that from the code. So technically, it's not self-attention, but it's calling the multi-head attention class, right? And so okay, so we need two multi-head attention classes instantiated here, and we have feed-forward neural network here, okay, and we need 3-layer normalization, right? 3-layer normalization, 3 green bars, right? And two multi-head attention, right? 2 multi-head attention, and one feed-forward neural network, one feed-forward right here. And there are 2 feed-forward here, but there's only one here, each decoder, right? And you have 3 dropouts. Okay, we need 3 dropout classes. Okay, so then we stack them together. This is how we do it. So we do that attention 1, attention wait block, and you pass in the XXX. Again, that's the same thing. But now instead of just the mask, we're passing in the look ahead mask. Okay, we have 2 types of masking. Remember that. Okay. Someone has very loud music passing by. I live in the Bronx. So this is one mask, okay? And this is another mask. We have two types. One is passing to the encoder, okay? One is passing the decoder. And decoder needs this create-look ahead mask. It can only use the past, right, ones that the model can only see the past ones, not the future ones, basically. And that's the purpose of doing language modeling in the decoder's case, right? So okay, so then we have one dropout, the first dropout, okay? We pass in the ATTN1 to here, and again, we're in the training mode. So passing the self.drop1, and we do layer normalization here, right? Add and layer norm, okay? And you have output 1. So this is, after this is output 1, right? So like cutting this off, that's this out 1. Okay, ATTN2, ATTN waits block 2, and we're calling this self.mha2 right here. Okay, and we instantiate that with, so we're calling that with encoder output, and output 1. Okay, so remember this is this. 1 second. Did I miss that? Where is yes. So this is V, the first one is V, the second one's K, and third one's Q. So VKQ, okay? And let's look back to our decoder layer. So this is V, and this is K, and this is Q. Remember, Q comes from the previous self-attention layers outputs. And that's this output. Remember, we said that, right? So, and this K and V comes from the encoder output, okay? The encoder output. And then we have the padding mask right here. So now we use the padding mask for this instead of look ahead mask. And we have another second dropout here. And we do the second layer normalization, which is here. So we're up to this point now. And we have the feed-forward neural network. Again, it's right here. And we have the third dropout, okay? And we have the third layer normalization, and that's the third green bar right here. Then you have your outputs. Okay, so it matches exactly bar by bar on this graph. It's amazing. Great. So any questions? Is that clear? Any questions before we go ahead? That's the encoder layer and decoder layer. Okay, seems like we don't have questions here. Okay, so now we actually remember we only build one encoder layer and one decoder layer. Okay, so now we got to stack them up to 6 encoder layers and 6 decoder layers, and that's another class. Okay, so now we say, okay, we have an encoder, the entire encoder structure. Okay, the entire encoder structure as a class instead of just one encoder layer as a class. So and then we just need to stack them up, right? So, and that's what we are doing here. We have self.d model, number of layers, right? We got 6, right? So self.embedding. Okay, so now we have the inputs, right? And input and input embedding. right here, input vocabulary size, and demodel. And we have the position encoding right here. So now we're talking about this part, right? Embeddings, position embeddings, okay? And position embedding, we're calling the position encodings function, right? And we pass that into the instance method. Okay, then we're just calling a list comprehension to instantiate 6 encoder layers and passing in the methods, all the methods instantiated here. And because we're not necessarily using them across the class, I believe that's why it's not using the self dot number of layers, self dot everything. And it's just using a list comprehension to generate a bunch of encoder layers and pass that into a class, into a list, and pass that into an inc layers instance variable with the number of layers, right? And you have your self dot dropout. Okay, so that's pretty straightforward. We're literally just stacking 6 encoder layers together. Okay, so sequence length in this case is tf.shape x1. So and that will be 512, I believe, because that's just the model. And adding, embedding, and position encoding. So we're doing exactly this step now. Adding, right? So x equals to self.embedding x. Okay, we're passing x into that. And that's batch size, input sequence length, demodel. And in this case, just should be, if I remember correctly, this should be 64 512 512. 64 512 512. Okay, then we times equal tf.mat square root of that. What is this? Times equal square root tf.cast. Okay, I need to understand this step a little better, but I understand this because that's just adding the position encoding right here. And okay. And you're doing the dropout here. And for the number of layers, you're doing the x equals to self.encode inc layers. And you pass that in, and you have your encoders outputs. I believe that's what it is. It gets a little more complex when you stack everything together. Okay, so. Okay, decoder. Again, we're creating a decoder class that would stack all 6 decoders together. Okay, and we have the D model, number of layers. Again, it's 6. And we have it embedding, we have positional encoding. It's the same thing, right? Doing a list comprehension, pass that into deck layers, dropouts. Doing that, yeah, it's basically the same thing. And interesting, so decoder layer also has position encoding. So so you also have that for decoder. And for I in range self.number of layers, you call the decoder layer I, you index that attention weights, and you pass in the attention weights. Okay. All right, then that's everything. And then you create another class to create the transformer. So you just like, you know, refactoring everything, right? Refactoring your code. Okay, so now we have all the encoder layers in one encoder class, which is here. And we have all the decoder layers in one decoder class, which is here. And then we pass in these two into like its own instance variable. And you have a final layer as a dense layer. And you just literally call them outputs, self.encoder, inputs, training, encoder padding mask. And you have deck outputs, attention weights, self.decoder. That's, and you have final output, deck output into the self final linear, and that's this, right? This is the final linear layer that's defined right here. And you output that. Okay, so we literally built up all the architecture here in this graph. And now we're gonna set the hyperparameters. In this case, oh, we're using 4 instead of 6. But I guess someone puts 4 here. That's fine. And number of hits 8, number of heads 8. D model, I don't know why it's changed here. It should be 6. DFF 2048. I think it was just someone was just trying to change the value, but this should be 6, right? It says right here. D model should be 512. DFF should be 2048. Number of heads is equal to 8. Input vocabulary size is token dot vocabulary size plus 2. I don't know what that plus 2 is. Target vocabulary size, token vocabulary size plus 2, dropout rate 0.1. So these are all the hyperparameters, okay, that you can tune. And then we have the optimizer. So you define your optimizer class, okay, custom schedule, and you inherit that from a learning rate schedule and initialize that here, self.dmodel equals dmodel. You set your warm-up steps 4,000. And we're using Atom Optimizer, okay, with a customized learning rate scheduler.
Wencheng, what's a warm-up step? I haven't come across that before.
It's right here. It's the way how you calculate your learning rate is D model times minimum of step number and step num times warm-up steps to the power of negative 1.5. It's just another parameter that you can, you know, they call it warm-up step, but basically I believe it has to do with how you increase and decrease your learning rates. And each step is an update. Each step is one time of gradient descent. So like after I think you probably change your learning rates in a way that perhaps it's increasing for like 4,000 steps, 4,000 updates. Then you perhaps decrease in a way. It's just a way to schedule your learning rates without, you know, so instead of using a constant learning rate, your scheduled learning rates to be, you know, increasing for number of steps and decreasing after that. Something like that. That's it. That's an example that FastAI uses. It's also called FastAI calls it learning rate annealing, and yeah. So Did I answer your question, John?
Yeah, thanks. I'll look into it in the fast
Yep.
table.
And you can see here, right? It's right here. 4,000 steps is right here. So, you know, right? So you warm up for 4,000 steps, you increasing your learning rate for 4,000 steps, and you kind of just gradually decrease that. And it's also called learning rate annealing, okay? $4,000 steps, okay? So loss and metrics. So we have our losses right here, sparse categorical, cross entropy. We're using cross entropy as our loss function. From logits equals to true. And loss object, real prediction, mask, that. Okay, so that's just basically, you know, calculating your loss function. And I don't know why we still need a mask here. Does anyone understand why we need a mask here? This is interesting. Someone? Does anyone know why we need a mask? Says, since the target sequences are padded, it's important to apply a padding mask when calculating the loss. Padding mask when calculating the loss. That's interesting. Okay, I didn't realize that we need a mask in the loss function as well. Okay, but because the target sequences are padded, so we need that. Okay, well, training and checkpoints. I mean, let's see how much we have left. It's 12:26. Yeah, so this is the training step, literally. And I don't think we have very good accuracy here. We literally have like 33, 34%, because we're doing, I think it's a relatively small data set, and we're not doing many steps either. This is just a showcase. That's why the accuracy is relatively low. And this is relatively straightforward. You're just like basically per batch inputs target variable and train step. Then you print the results out, and you make sure you have your checkpoints saved. And the way how you define that is that, so TensorFlow has a checkpoint manager that allows you to save checkpoints so that perhaps you can, you know, look back into it. Okay. And this is the training step function. Okay. And you calculate your gradients, you apply your optimizer, and you get your training loss, your accuracy, and you pass into a for loop. So this is pretty straightforward stuff. I don't think I need to. Yeah, we can probably go through the evaluation ourselves. Okay, that's it.
Hey, Wenchang, so last question. Do you know what the gradient tape is? I haven't come across that either before.
Gradient tape. It's here. Tape down.
Yeah, line 19.
It's just this gradient, tf.gradient tape. Let's look it up. Record operations. you're taping the gradients. So you're recording the operations for automatic differentiation. So you're just recording the gradients down. Operations are recorded if they're executed within this context manager and at least one of their inputs is being watched. Interesting. So you're recording the operations, and instead of just letting them pass by. And that's why you kind of need a context manager, right? Because once the context block is done, it's automatically closed. And it says right here, by default, the resources held by a gradient tape are released as soon as gradient tape.gradient method is called to compute multiple gradients over the same computation, create a persistent gradient tape. This allows multiple calls to the gradient method as resources are released when the tape object is garbage collected. So is that clear, John?
It is. I'll need to look into it a little bit more, but yeah, thank you for that.
Yeah. Okay, anyone else? Yeah, that's as deep as I could go. And
hey, no, you did a brilliant job. Thank you for staying with us for 3 weeks.
Yeah, my pleasure. And hopefully, I explained some of the concepts clear. I know some of the concepts still need to be digged a little further, and some of the functions, TensorFlow functions, still need to be digged a little further. Some knots still need to be tightened, as I could definitely feel that, but it's not easy to and it's the first step, right? It's the first step to understand everything here. And this is the monumental paper and with the code right here. And by going through this once, I think we have a relatively good understanding of what's going on in each component of this architecture. And I think it will help us, it will build a good foundation for us to look at, architectures like BERT, which I actually did in the NLP papers group. And I'm going to do a series of talk on GPT with the same format, basically theory, intuition, mathematics paper, and code. So, I'll do that within the NLP papers group. So, yeah, if you're interested, feel free to join that. So, all right. So I'm gonna stop here. If no one wants to say anything else, this will conclude the 3 talks on the transformers, and I believe we'll